Right. So this class, as I said, will be solving problems based on thermal expansion. So this is the first question. We had already discussed this, that based on temperature, this is how volume of an object varies. V is V naught into 1 plus gamma delta T, where gamma is called thermal coefficient of volume expansion. Okay. So suppose you take an object and start changing its temperature, whether you increase or decrease, this is how volume varies with temperature. Fine. Now, as you raise or decrease the temperature, the mass of the object is not going to change. Its volume may increase or decrease depending on what you do to the temperature. So, mass remaining same and volume changing means density changing. Okay. So, I want you to derive how density varies with temperature. Okay. You can assume mass is m. Okay. It will remain the same. Initial density is mass by volume. No. So, density before the temperature change will be mass by original volume. Density after temperature change will be mass by final volume. And I want you to relate final density to initial density. In that process, mass will get cancelled. Okay. Try this, both of you. I'll give you 2 minutes. So initial density is mass divided by initial volume. And after the temperature change, final density not into 1 plus gamma delta T. Now we need to relate these two. So best is to divide the equations. Mass will get cancelled. Therefore, rho divided by rho naught if you do. Okay. So delta T divided by m by v naught. M and v naught will get cancelled. That's all. So you get rho is equal to rho. Okay, this is correct. But see, the denominator 1 plus gamma delta T, you can send it to the numerator. Okay. You can write rho is equal to rho naught into 1 plus gamma delta T whole to the power minus 1. Okay. And this is why I asked you to revise what is 1 plus x whole power n. Can one of you quickly tell me what is 1 plus x whole power n approximately equal to? When n is very small, sorry, when x is very small compared to 1.
1 plus n into x.
1 plus n into x, correct. Okay. Now you observe what you have in this bracket. 1 plus gamma delta T whole power minus 1. Okay. So you can treat gamma delta T as x and minus 1 as n. The gamma values we had seen few classes earlier. For steel, it was 10 power minus 5. Okay. Of that order. Usually for solids, it will be around that much only, 10 power minus 4, 10 power minus 5. So gamma delta T is going to be a very small number compared to 1. Okay. So we can apply this approximation. And in place of n, we have minus 1. Therefore, density can be written as rho naught into 1 minus gamma delta T. That's all. This is how density varies with temperature. So volume, it is V naught into 1 plus gamma delta T. Density will be rho naught into 1 minus gamma delta T. So if we raise temperature, volume increases, density decreases. Okay. And you can readjust this equation also. Rho naught minus rho naught gamma delta T. No? So send rho naught to the other side. You get rho minus rho naught is equal to minus rho naught gamma delta T. Now divide by rho naught. Rho minus rho naught divided by rho naught is gamma delta T. You can write it like that also. Fine. Let's consider another situation based on this, based on thermal expansion. Right. Consider a frame like this. Okay. Assume it is a metal frame. So basically a metal sheet which has been cut out in this shape. Okay. Let me mark some dimensions here. Let's say the distance from here to here is A. This is B. The length of the outer is C. Okay. So the question is that if the temperature of the frame is raised, what happens to A, B, and C? Means, will they increase, decrease, or remain same? Each one you have to answer separately. Okay. Will those lengths, which of those lengths will increase, which will decrease, and which will remain same? If you think all increase, you can say all increase, and so on. Okay. Think about it carefully. I want all of you to give answers in the chat. I'll give you 2 minutes. Recollect what is thermal expansion fundamentally. Okay. Based on that, you'll be able to answer this problem. Right. So we are increasing the temperature of this metal frame. Now, basically what happens at the molecular level, when you increase temperature, the molecules will need more space between them. Okay, because amplitude of molecular vibrations increases. Now consider some molecules of this system. Okay. Let's first think of what happens to A. That is where most of you were confused probably. Consider two molecules. Okay. Let's say this one and this one. They need more space between them. Okay. Actually, there's a continuous chain of molecules. Fine. Like this. They need more space between them. And how will they get more space between them? By moving away from each other. Okay. So you consider this once. All the molecules between them need more space around them. Then definitely these two, okay, you can call this molecule as X, this one as Y. X and Y will need to have more gap between them. Okay. So definitely it will expand. That dimension A that we had marked, it will increase. Fine. One of you said because there is free space here, okay, inside the metal frame, there is some free space, so some molecules will come into that space. Uh, had the situation been like this, just a moment. Consider this as one frame and this as another frame. Had they been free like this, okay, and you raise the temperature, then what will happen? Because they are free to expand in all directions, they will expand this side, these molecules moving to this side, and effectively the gap between them will decrease. But the problem here is that these two are attached, okay, by metal like this. Then that kind of expansion cannot happen. They are not completely free to expand inwards, okay, because there is obstruction in between, and that obstruction also has to expand, no? So effectively this is how it expands. Okay, and what Vanilla said is correct. Thermal expansion works like photographic zoom. So if there is empty space inside, empty space means cavity. If there is a cavity inside, as if the cavity also was filled with the same material. Fine. What we mean is, suppose this gap was filled with the same material which is surrounding it, then the entire plate would have expanded. So even if that gap it is expanding. Okay. So yes, remember that thermal expansion works like photographic zoom. In case of isotropic materials, okay, which have same alpha in all directions, this is how it works. So effectively what is happening? A is increasing, B, which is the length of this outer edge, is increasing, and C, which is the gap between outer edge and inner edge, that C is also increasing. All dimensions will increase. And if you decrease temperature, all dimensions will decrease, provided the material is isotropic. Okay. Next question, just a moment. Right. Consider a container like this, which is completely filled with liquid. Okay. So effectively, we can say that volume of the container is almost equal to volume of the liquid. Okay. Now, container is made of one material, liquid is obviously a different material, and different materials have different gamma values. Let's say container's gamma value is gamma C. Gamma means coefficient of volume expansion. Okay. And liquid's gamma value is gamma L. Okay. Now, based on your imagination, you tell me, and okay, let's make an assumption first. Suppose gamma of container is greater than gamma of liquid. Fine. In that case, based on your assumption, you all, imagination, you all tell me, what will happen if we raise the temperature? What will happen means, what are the cases I want you to consider? Will the container still be fully filled with liquid? Or will the liquid overflow? Or will there appear a gap in the container? Okay, that means some free space will appear in the container. What do you think will happen in the case where gamma of container is greater than gamma of liquid and temperature is raised? Okay, think carefully, type your answers in chat. I'll give you 2 minutes. If you want to unmute and tell also, you can. Fine. I got one answer as free space appears in the container. Vanilla, can you explain this? Like last question, you said thermal expansion is like photographic zoom. Now, if you use the same logic here and just zoom into this picture, free space will not appear, no? Then how do you justify your answer? Your answer is correct only, but how do you justify it?
The gamma of the container is more than gamma of the
Correct.
water.
Okay,
So
okay,
it
fine,
will expand.
fine. See, the material, like whatever is expanding here, is not the same material throughout. Okay, the previous question, there was a metal frame expanding, cavity inside, but it was the same metal everywhere. So the same relative expansion happens everywhere. But here, The liquid part has a different gamma value compared to the container part. Fine. So they will not expand in the same manner. And it is given to you in this case that gamma of container is more than gamma of liquid. So we know that final volume is initial volume into 1 plus gamma delta T. Initially, liquid and volume were occupying the same volume. Sorry, initially liquid and container were occupying approximately the same volume. Okay, but whichever has a higher gamma value will expand more. And we are taking the case where gamma of container is more than gamma of liquid. So container expands more than liquid. As a result, what will happen? You will see a gap in the container. Okay. So what happens is something like this. Yeah. Both the container and liquid expand. Okay. I'm not saying that liquid is not expanding. Liquid will expand, container will also expand. Let me compare both the diagrams. So originally it was like this. Less liquid, less volume of container. Finally, it will be like container volume increases, liquid volume increases, but container increases, expands more than liquid. So relatively, I mean, it will appear as if the level of liquid has gone down. Okay. So relatively, the liquid appears to contract. It didn't actually contract, but with respect to container, if you see, it appears to contract. Okay. That is what happens. Next case. Next case is quite obvious. Suppose gamma of liquid is greater than gamma of the container. In that case, liquid will expand more than container. And if liquid expands more than container, like relatively, not relatively, both of them will expand, but one expands more than the other. So both expand and liquid expands more than container. Container cannot hold excess liquid. No. So what will happen? You will see some liquid overflowing. Right? That is what will happen. So relatively or apparently, the liquid expands. Okay. You can even tell how much liquid overflows or what is the volume of the free space that is created here. Okay. How do you calculate this volume? Can any of you tell me? Suppose gamma of container was more than gamma of liquid. How to calculate how much free space is created? How to find out how much empty space is there in the container? Very simple. Volume of container minus volume of liquid will give you the volume of that empty space. That's all. Okay. So we can write final volume of container is initial volume into 1 plus gamma of container delta T. And final volume of liquid is initial volume of liquid. Initial volumes were same. Okay, we assumed that initially the container was fully filled with the liquid. 1 plus gamma of liquid delta T. Okay. Now if you want to find out apparent expansion of liquid, fine, you write the equation like this. Apparent expansion or relative expansion means how much extra the liquid has expanded with respect to container compared to the container. So apparent expansion of liquid can be calculated like this. Final volume of liquid minus final volume of liquid minus final volume of the container. And how do you write an equation for this? V naught into 1 plus gamma of liquid delta T minus V naught into 1 plus gamma of container delta T. V naught is common, then the brackets, if you subtract 1 plus gamma L delta T minus 1 plus gamma sigma, 1 and 1 will get cancelled. You get gamma L minus gamma C delta T. This is apparent expansion. So apparent change in volume. So if gamma of liquid is more than gamma of container, apparent expansion will be positive. So if this bracket is positive, apparent expansion will be positive, liquid will overflow. Suppose gamma of liquid is less than gamma of container. This will be negative, this will be negative, means apparently the liquid contracts. That's all. So this is called apparent expansion. And this bracket here, gamma of liquid minus gamma of container, can be taken as apparent gamma. Okay, means apparent or coefficient of apparent expansion. You can write it like that. Simple logic. But remember, all this is valid only when their initial volumes are equal. Okay, we are taking V naught common here in this expression if you observe. Okay. Then only you can write apparent gamma is gamma of liquid minus gamma of container. So initially, if it is completely filled, you can use this logic. Okay. Next problem. Suppose there's an object floating on a liquid. Can one of you tell me the condition? When does an object float on a liquid? We had discussed this in fluids. When density of object is less than density of liquid, the object floats. Okay. So let's assume the object is some randomly shaped object like this. And we know that floating doesn't happen with the object being completely outside the liquid. Partial immersion must be there. Okay. If you visualize the volume that is immersed, we had learned this also in fluids that volume immersed to total volume. This ratio is basically density of object by density of liquid. So suppose density of object is half the density of liquid, half volume will be immersed. Okay, out of the total, half volume will be immersed. If density of object is one third the density of liquid, one third of the object will be immersed. Two thirds will be outside. So that ratio we can find out. Okay. Now, if we raise the temperature of this system, okay, raise or decrease, if we change the temperature of this system, densities will change because if you change temperature, volume changes, and if volume changes, density changes. Today itself we discussed, okay, the first question that we solved today was how density varies with temperature, and we got rho is equal to uh, initial density into 1 minus gamma delta T. Okay, so let's say the situation is like this: object is floating on the liquid and it is told to you that first case, gamma of the object is more than gamma of liquid. Ignore expansion of container now. Okay, because what we are interested in is what happens to the object, whether it sinks more or rises more. Okay, that is what we want. So containers expansion is immaterial now. How much sinks or how much volume will be immersed depends on densities only. No, it doesn't depend on how much water is present. Okay, it only depends on ratio of densities. So you don't have to bother about the container. Suppose density of object is more than density of liquid. Oh, wait. What am I saying? Gamma of object is more than gamma of liquid, and we raise the temperature. Okay. What will happen to the ratio of volume immersed? Will the ratio of volume immersed increase or will the ratio of volume immersed decrease? Means relatively, will the object sink more or come out of the liquid? That is what I'm asking. Okay. Think carefully and answer. I'll give you all 3 minutes. I want answers from all of you. In 3 minutes, whatever answer you get, type it in chat. Remember, gamma of object is more than gamma of liquid, and we are raising the temperature. So what happens? Right. Let's discuss the answer. I got one answer as the immersed volume decreases. Fine. See this. I mean, I have given you the formula also here. Fraction of volume immersed only depends on this density ratio. So you just have to think of what happens to this ratio when you raise the temperature. Let's see. Now, initially they had some densities. Density of object was less than the density of liquid. That is why it was floating on the liquid. Okay. Now, final density of object will be initial density of object into 1 minus gamma of object delta T. Simple. The equation is given to you on the screen. Final density of liquid will be initial density of liquid into 1 minus gamma of liquid delta T. Now, the ratio of volume immersed, or the fraction of volume, I should not call it ratio, fraction of volume immersed depends on this ratio. So, divide these two. Final density of object divided by final density of liquid. Okay. That initial ratio, whatever is there, is there. Now, this ratio, rho naught by rho L, is initial fraction of volume immersed. Okay. Fine. That initial fraction is now multiplied with 1 minus gamma naught delta T divided by 1 minus gamma L delta T. Now it is given to you in the question that gamma of object is more than gamma of liquid. If gamma of object is more than gamma of liquid, there is a minus sign here, then the numerator decreases more than the denominator. Okay, because gamma naught is a greater number, but there is a minus sign, the decrease in the numerator will be more than the decrease in the denominator. Fine. So basically what happens, this value 1 minus gamma naught delta T will be less than this value. Okay. So effectively what is happening here is the initial fraction of volume immersed, whatever is there, that initial fraction is getting multiplied with a number less than 1. And if you multiply anything with a number less than 1, okay, means positive number less than 1, well, its value decreases further. Okay. So basically the final answer is less than the initial fraction. Fine. So finally, the fraction of volume immersed will be less than the initial fraction of volume immersed. What does that mean? You will see the object relatively coming out of the liquid. Fine. Suppose initially the fraction of volume immersed was 2/3. Finally, it will be lesser than that. So maybe 2/4 or 2/5. It depends. It depends on temperature and temperature change and all. Okay. But the fraction will decrease, and this is how you comment on it. That's all. It's quite simple. First thing you need to know is on what basis you can tell the fraction of volume immersed, and that is nothing but density of object by density of liquid. Now you just have to find out what happens to that ratio after the temperature change. Okay, so if object's gamma is more than the liquid's gamma and you raise the temperature, relatively the object is going to come out. Okay, the fraction of volume immersed decreases. And reverse, if you decrease the temperature, then you know what is going to happen. If you decrease temperature, no, delta T will be negative. Then negative of negative effectively becomes positive. And since gamma naught is more than gamma L, numerator increases more than the denominator. Okay, then that fraction will become more than 1. I mean, that ratio will become more than 1. Then the fraction will increase. So you will see it sinking further. Okay, so a little bit of mathematics is involved. But hope you all understood. If you have any doubts, you can ask. So if they want to frame very tough questions based on thermal expansion, including fluids, they can do such things also. They can ask you, like, initial ratio can be given. Maybe initially 1/3 is immersed. They can ask you, what should be the temperature change such that 1/5 is immersed? Okay. But not a big deal. You can solve. Okay. So we have discussed apparent expansion. We have discussed thermal expansion working as photographic zoom. Fine. This much is enough about thermal expansion.